So these are the models for estimating how we price the products of insurance companies. And there are some issues there of what interest rate to use and what the actual amount of taxes will be and so on. But the very basic model is just the model of estimating the pure cost of insurance, how much we'll pay for that. This is the starting point. And then building on that, we will add the costs of other things, capital costs, expenses, and taxes. At the very core of non-life insurance mathematics lies the basic model proposed in 1903 by Philip Lundberg, a Swedish actuary. The amazing thing about this model is that he produced the model and some basic estimates of the probability of insolvency of an insurance company before the Lebesgue's theory of integral and measure theory. But I think it was 1904, a year later, that the Henri Lebesgue developed his theory, and then around, I think, something like 1912, there was a very famous Polish mathematician, Hugo Steinhaus, who was walking in Krakow in the park and heard two young people talking about Lebesgue integral. Now, you know, that's really astonishing when you have young people who looked almost high school age talking about Lebesgue integral in a park in Krakow, in Poland. Well, there was no Poland in 1912, but what used to be Poland and what later became Poland. And one of those people was Stefan Banach, whom Hugo Steinhaus kind of adopted and made him become a professor with him at the University of Lviv, or Lemberg as it was called then, because it was part of Austro-Hungarian Empire, which soon disappeared. And it turns out that the theorems that Lundberg proved were incomplete, the proofs were limited, but you can prove everything that Lundberg did, and his main theorem about probability of ruin of an insurance company using the fixed point theorem of in Banach spaces developed by Stefan Banach. So these people were tremendous influence on each other. It was an amazing period when a lot of very great mathematics was created. So the model assumes that claims happen at times T1, which is less than or equal to, greater than or equal to 0, T2, and so on, called claim arrival times, or claim arrivals, or claim times, or arrivals. When the claim arrives at time Ti, its claim size, also called claim severity, is a random variable xi with a random variables xi assumed independent and identically distributed. The processes Ti and xi we call a collection of random variables a random process, especially if they are indexed by time. And here, the times Ti correspond to the amounts xj, and they are two things that are happening at the same time, and they are forms of stochastic processes. They are assumed to be independent. The stochastic process describing claims number n of t is the number of claims occurring up to time t, so that n of t is the maximum of I such that ti is less than or equal to t. Total claims amount is s of t equal sum from I equal 1 to n of t of xi, which is basically, we add up all the claims that happened up to that point in time. Note that we need to have some form of estimate of the value of the random variable for the purpose of projecting claims and expenses for pricing and for reserves. The most commonly used process for the claim count is the Poisson process. So I want to remind you about this very important probability distribution called the Poisson distribution, and that was part of the notes about discrete probability distributions, and I'll open that again to remind you. So I'm going to stop sharing and open the other notes to remind you. And in that, we had these things that we already mentioned, the Bernoulli trial, binomial distribution, geometric distribution. We discussed that, negative binomial. But the very end was the Poisson distribution. In that distribution, the probability of hitting the value of n, where n can be 0, 1, 2, and so on, is e to the minus lambda times lambda to the n over n factorial. And lambda is the parameter of that distribution, which is equal to the expected value of it and the variance of it. This is the most commonly used probability distribution for counting insurance claims. This is very, very important, and you need to know this probability distribution and be familiar with it. So I'm going to come back to my regular notes, except that, okay, fine. And the probability generating function of the Poisson distribution. So I probably should remind you what a probability generating function, or PGF, is. And I'll just write this in just a moment. Okay. So for a random variable k, and we will only look at discrete random variable, the probability generating function is something that is defined this way, that it's the sum from k equal to 0 to plus infinity of probability that n is equal to k times z to the k. In general, it's, actually, I should say what it is in general. It's the, so P sub K of Z is equal to the expected value of lowercase z to the power of the random variable k. This is a concept used for describing probability distributions. It's a bit similar to what is the moment generating function, which I sometimes mention. Okay. So here it is for this random variable, the probability generating function, it's a sum from k equals 0 to plus infinity of lambda to the k over k factorial e to the minus lambda. That whole expression is the probability that this Poisson random variable is equal to k times z to the k. And then if we put e to the minus lambda in front of it, this becomes the sum from k equal to 0 to infinity of lambda z to the k over k factorial. That is exactly equal to e to the lambda z. That's the power series expansion of the exponential function for the number lambda z. So the probability generating function of the Poisson distribution is equal to e to the lambda times z minus 1, where z is that variable, artificially introduced variable of the probability generating function. So this Poisson distribution has this important property that if n1, n2, up to nn are independent Poisson random variables with means lambda 1, lambda 2, up to lambda n, then the sum of them, but remember they are independent, is Poisson with mean lambda 1 plus lambda 2 up to lambda n. That tells you something that is very interesting. Even though this is a discrete distribution, if you add up a lot of Poisson distribution random variables, you get a Poisson distribution with a very large parameter lambda. For very large values of parameter lambda, the Poisson distribution starts resembling the normal distribution. That's a consequence of the central limit theorem. And you can easily see this by considering the probability generating functions. That's actually, and I'm trying to see why, because otherwise I don't, oh, okay. Okay, I actually tell you at the beginning. Okay, I didn't need to tell you all this because I told you at the beginning that probability generating function of a random variable x is defined as expected value of z to the x. Moment generating function is defined as expected value of e to the tx and also may not exist. So the probability generating function or moment generating function of a probability distribution exists. If it exists, then it determines it uniquely and completely. We also have this important inverse property called the decomposition of Poisson distribution. I probably should have said distribution here. Let n be a Poisson random variable with mean lambda. Assume that each occurrence of this random variable can be classified into one of m types with probabilities p1, p2 up to pm independent of other events. Then the numbers of occurrences of each type, n1, n2 up to nm, corresponding to occurrences of types 1 up to m respectively, are mutually independent random variable Poisson random variables with mean lambda p1, lambda p2 up to lambda pm. And the reason why we discuss Poisson distribution is to use it for counting claims in insurance. So a discrete stochastic process is called a counting process if it can be used for a claim count for insured claims at each time of its occurrence. A counting process is called a Poisson process with rate lambda if n of 0 is 0. So at time 0, we start the count, we have 0 claims. The process has stationary and independent increments, and n of t has Poisson distribution with a mean lambda to t. A difference of two values of a stochastic process at two different times is called an increment. Stationary increments, that means that the difference n of t1 plus h minus n of t1 and n of t2 plus h minus n of t2 have the same distribution. So you see that these are changes in value of the process at two different points in time, but they have the same probability distribution. That's the probability distribution that we analyzing, right? How does it happen? Well, that's the property that we want, that the length of time interval tells you what the distribution is, and it doesn't matter where that time interval is. Now, independent increments that means that n of t1 minus n of t0 and n of t3 minus n of t2 are independent if the time intervals t0, t1, and t2, t3 are non-overlapping. So this is what we want. We want a process that starts at 0, the increments are stationary and independent, and the n of t has Poisson distribution with mean lambda t. Of course, this means that n of s plus t minus n of s also is Poisson with mean lambda t because the stationary increments. Because the random variables n of s plus t minus n of s and n of t minus n of 0 have identical distributions. And of course, n of 0 is 0 and are independent if they are non-overlapping. Here is an equivalent definition of a Poisson process. A counting process is called a Poisson process with rate lambda if n of 0 is 0, the process has stationary and independent increments, and the probability that n of h is 1 is lambda times h plus little o of h. O of h is any quantity such that O of h divided by h goes to 0 as h goes to 0. So something that is substantially smaller than h. And the probability that n of h is greater than or equal to 2 is O of h. Now consider a situation where when we count claims received by an insurance company, we start counting at time 0 and let t1 be the time of the first claim and t2 be the time between first claim and the second claim, and so on, with Tn being the time from the n minus first and the nth claim. Then these random variables Ti so created are called inter-arrival times or waiting times. These are waiting times for next claim. For a Poisson process, the inter-arrival times are independent, identically distributed exponential random variables with hazard rate lambda. If we denote by S sub n the sum from I equal 1 to n Ti, the waiting time until the nth claim, then S sub n has the gamma distribution with parameters alpha equal to n and beta equal to lambda. So we already talked about the exponential distribution, and it shows up over and over in description of what we're working with. But what I'm noting to you is also that if you add independent exponential distributions, then and you assume that they are independent, identically distributed, then the sum of them has the gamma distribution. And the gamma distribution has two parameters. One parameter is the hazard rate of those exponential distributions that we're adding, and the other parameter is the number of those exponential distributions that we're adding. In particular, if PDF of it is of this form: lambda e to the minus lambda t times lambda t to the n minus first power over n minus 1 factorial. So I don't expect to demand that you memorize this probability density function of the lambda of the gamma distribution. I'm sorry, of a gamma distribution. However, I want you to be aware of this fact that if you add exponential distributions that have that are independent and have the same hazard rate, the same mean, then you get a gamma distribution. Now consider a Poisson process occurring at the rate lambda. Assume that the events counted by the process are of type 1 with probability p and of type 2 with probability 1 minus p, independently of all other events. We write n of t to be n1 of t plus n2 of t, where n1 of t counts type 1 events and 2 of t counts type 2 events. Then n1 of t and n2 of t are both Poisson processes with respective rates lambda p and lambda 1 minus p, and the two processes are independent. And this is the same thing as this previous kind of You add up Poisson distributions under certain conditions, you get Poisson. And if you split the Poisson into different types of events, each of them will be Poisson. This is the same idea. A non-homogeneous Poisson process differs from a homogeneous Poisson process with constant rate lambda for the homogeneous one, in that its claims intensity is a function of time. In other words, the lambda is a function of time. Claims intensity is in general defined as lambda of t equal to the limit as t goes to, it's epsilon that we're using here. So epsilon going to 0 of the expected number of claims in t minus epsilon over 2, t plus epsilon over 2 divided by epsilon. Or effectively, lambda of t is the derivative of the expected number of claims, and the expected number of claims is the integral of lambda of t. In general, in order to get the expected number of claims in a time interval AB, we take the integral of claims to get the, we take the integral of the claims intensity lambda of t from A to B. Over very small intervals, the claims intensity is approximately constant, and therefore number of claims is approximately Poisson. We can add up small disjoint subintervals, and due to independent increments, we end up adding up independent approximate Poisson distributions to obtain an approximate Poisson distribution. In general, the number of claims in a time interval AB equals the integral of the claims intensity from A to B, and that's written as M. The cumulative distribution function f sub t of the waiting time until the claim happens can be written in terms of claim intensity as f sub t of t equal to 1 minus e to the minus integral from 0 to t of lambda of s ds. So for example, if lambda of t is equal to 20t cubed, then f sub t of t is 1 minus e to the minus integral from 0 to t of 20s cubed ds. Okay, 20s cubed is a function that is a derivative of 5s to the fourth, and 5s to the fourth evaluated from 0 to t gives us 5t to the fourth. So this is 1 minus e to the minus 5 to the fourth. The resulting distribution in this case is called the Weibull distribution. And the survival function of the waiting time until the occurrence of a claim in general is, I probably should separate this because it's this. S sub t of t is e to the minus integral from 0 to t of lambda of s ds. If there is a claim at time s, then the time of the next claim is distributed as follows, that f sub t, the cumulative distribution function of t, is 1 minus e to the minus the integral from s to t of lambda r dr. So for example, for this lambda of t equal to 20t cubed, the probability of having no claim between time 0 and times 0.5 is the probability of 1 minus big F. So 1 minus what we just said above, and that's e to the minus 0.4 to 0.5 of 20t cubed dt. So that's e to the minus 5 t to the fourth from t equal to 0.4 to t equal to 0.5, and that's equal to e to the minus 1.845. The exponent 0.1845 is the expected number of claims between the times 0.4 and 0.5. It kind of plays the role of lambda in this case. Now, we'll look at those inter-arrival times and waiting times for non-homogeneous Poisson processes. For homogeneous ones, they are exponential. The waiting time for the first claim has the cumulative distribution function of 1 minus e to the minus lambda, e to the minus integral from 0 to x of lambda of t dt. And we called this thing m of x before, so this is 1 minus e to the minus m of x. The integral from 0 to x of lambda of SDS is called m of x, so that m prime of t is equal to lambda of t. That follows from the fundamental theorem of calculus. The PDF of the waiting time for the first claim is the derivative of the CDF. So that's going to be equal to, if we write it as t, that's going to be m prime of t e to the minus m of t, and that's equal to lambda of t e to the minus mt. The mean expected waiting time, so mean time or expected time for the first claim is computed by integrating the survival function s of x, and that's another application of the Darth Vader rule. So the expected value is the integral of the survival function, and the survival function in this case is equal to e to the minus m of x, and m of x is calculated as the integral of the lambda. So for example, if you have a non-homogeneous Poisson process with lambda of t equal to 2t, what is the mean waiting time until the first claim? So m of t is the integral of lambda, and it's equal to the integral from 0 to t of 2s ds. That's t squared. The mean waiting time until the first claim is the integral from 0 to infinity of e to the minus m of t dt. That's the Darth Vader rule. And that's equal to the integral from 0 to infinity of e to the minus t squared dt. That's not easy, but we can try to calculate it. Well, we do integration by substitution. We take y equal to t squared. When t is 0, y is 0. When t goes to infinity, y goes to infinity. And the derivative, t is equal to square root of y. So dt is equal to 1/2, actually 1 over 2 square roots of y. So that's 1/2 e to the minus 1/2 dy. So we plug it in, and we end up with the integral from 0 to infinity of 1/2 of e to the minus y, y to the negative 1/2 dy. Now, if you look up in Wikipedia what the gamma function is, that's what we're using here. This is the gamma function evaluated at 1/2 divided by 2, and that's equal to square root of pi over 2, because the gamma function evaluated at 1/2 is equal to a square root of pi. This is a trick using the gamma function, and it's not going to be tested. The gamma function is defined as the integral from 0 to plus infinity of x to the z minus 1 e to the minus x dx, but this is gamma of z. What happens to the mean waiting time if we double claim intensity? So if lambda of t goes to 2 lambda of t, that m1 of t, that is a result of doubling, is the integral from 0 to t of 2 lambda of s ds. That's 2m of t. So the expected waiting time is the integral from 0 to infinity of e to the minus 2m of t dt. And it's another example where we again are going to play with the gamma function. And again, you don't really have to be worried about it, but we're going to do this because it's educational. So for a homogeneous Poisson process with lambda of t equal to 4t, what is the mean waiting time until the first claim? So the integral of lambda of t equal to 4t is 2t squared. The expected value is the integral from 0 to plus infinity of e to the minus m of t dt. That's the integral from 0 to infinity of e to the minus 2t squared dt. And now we kind of stuck. That's not an easy integral to calculate. So I, again, do a substitution. Y equals 2t squared. Therefore, y over 2 is equal to t squared. So t is equal to the square root of y over 2. The derivative of t with respect to y is 1 over 2 square roots of 2, y to the negative 1/2 dy. Not simple, but it works. So we have what we need. Okay. Trying to see who is making noise. Sorry, I'm going to mute you when you make noise. Okay. All right. So we do the substitution. When t goes to 0, y goes to 0. When t goes to infinity, y goes to infinity. So this becomes the integral from 0 to infinity, 1 over 2 square roots of 2, e to the minus y, y to the negative 1/2 dy. That's equal to gamma of 1/2 divided by 2 square roots of 2. And guess what? Gamma of 1/2 is equal to square root of pi. Again, the same trick. But you have to know the values of the gamma function, so it's not going to be on your test. Now let T1 be the time until the first claim, T2 be the time from the first claim until the second claim. Then Ti is inter-arrival time for the ith claim, given that we observe the I minus first claim at time s, and it has the cumulative distribution function of this form. F sub ti of x equals 1 minus e to the minus integral from s to x plus s lambda of t dt, and that's 1 minus e to the m of s minus m of x plus s. Unless lambda of t is constant, as for homogeneous Poisson processes, the distribution of inter-arrival time ti for the ith claim depends on the time we observe the I minus first claim. In general, the inter-arrival times are neither independent nor identically distributed and may not be exponential, and it may get complicated this way. But for the simplest case of homogeneous Poisson process, they are independent and identically distributed. So now another example, given lambda of t equal to 3t squared, what is the probability of having 3 or more claims in the time interval from 0 to t? And we calculate that m of t is t cubed, so that using this as a parameter, lambda and Poisson distribution, probability of 0 claims is e to the minus t cubed. We replace lambda by that t cubed. Probability of 1 claim in 0t is t cubed e to the minus t cubed. Again, t cubed replaces lambda. So this is like lambda e to the minus lambda. Probability of 2 claims in 0t is t to the 6, which is t cubed squared, times e to the minus t cubed, because t cubed replaced lambda, divided by 2. So this would be like lambda squared divided by 2 times e to the minus lambda. Therefore, the probability of 3 or more claims is 1 minus the sum of these 3. So 1 minus e to the minus t cubed plus t cubed times e to the minus t cubed plus t to the 6 e to the minus t cubed over 2. Note that if there are 3 or more claims by time t, then the waiting time until the third claim is less than or equal to t. Thus, the cumulative distribution function for the waiting time until the third claim is the probability of having 3 or more claims from time 0 to t. In general, the cumulative distribution function of the waiting time until the nth claim is the probability of n or more claims from the Poisson distribution with mean m of t. So the probability of waiting time for nth claim is less than or equal to t is the probability that n or more claims happen in the time interval 0t, so that the CDF is equal to 1 minus the sum from I equals 0 to n minus 1 of e to the minus m of t to the I over I factorial, where we're adding up the probabilities of having those prescribed number of claims. To compute the probability density function of Sn, the time of the nth event, consider that the probability that Sn is greater than t and less than t plus h is the probability that n of t is n minus 1, and one event happens in t to t plus h plus O of h, some small addition. It's the probability of n of t equal to n minus 1 times the probability of one event in that time interval. And this is equal to e to the minus m of t to the n minus 1 over n minus 1 factorial, times lambda of t times h plus O of h, plus the other O of h on the outside. That becomes lambda of t e to the minus m of t times m of t to the n minus 1 over n minus 1 factorial times h plus O of h. And therefore, f sub n of f sub Sn of t is equal to lambda of t e to the minus m of t times m of t to the n minus 1 over n minus 1 factorial, where m of t is the integral from 0 to t lambda of s ds. Now recall that for a homogeneous Poisson process, the waiting time until the nth event follows the gamma distribution with parameters alpha equal to n and theta equal to 1 over lambda with a PDF that looks like this. I probably should move this to the, I'm trying to move this to the previous page, and this thing didn't make it easy. Okay, that's better. Okay. Now, we're going to, again, kind of reiterate this idea of what happens when you add up Poisson distribution and add up Poisson processes. So adding independent non-homogeneous Poisson processes on the same interval results in a new Poisson process with claim intensity equal to the sum of claim intensities of the two. I should have said, of the two. For example, if we consider 3 independent Poisson, actually of these processes, not the 2, because we're adding more than 2 of these processes. Okay, for example, if we consider 3 independent Poisson processes on 0 to 25 with the following intensities: lambda 1 of t is 6t cubed, lambda 2 of t is 10t cubed, lambda 3 of t is 4t cubed, then the sum of these processes is a non-homogeneous Poisson process with claim intensity equal to 20t cubed. Now, thinning of Poisson process is splitting it into sub-processes based on some criteria. So if we select at random a fraction of the claims from a non-homogeneous Poisson process, we get a new non-homogeneous process with smaller claim density determined by this fraction. If claims are from a non-homogeneous Poisson process and one divides these claims into subsets in a manner independent of the frequency process, then the claims in each subset are independent non-homogeneous Poisson processes. If original non-homogeneous Poisson process has claim intensity of lambda of t, and we select at random a claim that occurs at time t with probability p of t, then the selected claims are a non-homogeneous Poisson process with claim intensity lambda of t times p of t. And here's an example of that. So consider a non-homogeneous Poisson process with lambda of t equal to 20t cubed. Assume that frequency and severity are independent. So frequency is how often the claims show up, and severity is how big the claims are. And we basically assume that those are independent. We also have 30% of claims are of size less than 10,000. 50% of claims are of size between 10% and 10,000 and 25,000. And 20% of claims are of size larger than 25,000. What are the frequency processes for the claims of different sizes? So these are 3 independent non-homogeneous Poisson processes because these severity of claims are independent of frequency. And the claim frequencies are 30% of 20t cubed, that's 60 cubed, 50% of 20t cubed, that's 10t cubed, and 20% of 20t cubed, that's 4t cubed. Now here we will do an exercise, and it's probably a bit harder than what you could have on the test, but it's good exercise for you. For claims process, you are given the number of claims, n of t, is a non-homogeneous Poisson process with intensity function lambda of t equal to 1 for t between 0 and 1, lambda of t equal to 2 for t between 1 and 2, lambda of t is equal to 3 when t is more than 2. Claims amounts yi are independent and identically distributed random variables that are also independent of n of t. Each yi is uniformly distributed on the interval from 200 to 800. The random variable P is the number of claims with claim amount less than 500 by time t equal to 3. The random variable Q is the number of claims with claim amount greater than 500 by time t equal to 3. R is the conditional expected value of P given that Q is equal to 4. Calculate R. So we are doing what I just told you is the I'm sorry, just had something to the sudden that show up here. Okay. Okay. So, my apologies. For original process, the mean number of claims by time 3. Oh, I'm sorry. Let's just look at the second sentence because it's important. P and Q are independent Poisson random variables. Thus, the conditional expected value of P given a certain value of Q is just the unconditional expected value of P because of their independence. And for the original process, the mean number of claims by time 3 is the interval from 0 to 3 of lambda of t dt. And what is that integral? Well, the lambda is piecewise flat. It's a piecewise constant. So that's 1 times 1 minus 0 plus 2 times 2 minus 1 plus 3 times 3 minus 2. So it's 1 plus 2 plus 3 is 6. For the random variable P, the mean number of claims by time 3 is m of 3 times the probability of having a claim of less than 500. Okay. The probability that the claim is counted by P, so it's less than 500. So let's go back to the problem. And here it says that the claims are uniformly distributed on the interval from 200 to 800. Okay, so what are the chances of being less than 500? Well, 500 is how far away from 200? 300. And 500 is how far away from 800? Also 300. So it's a midpoint of the two. Well, it is a midpoint also because you see that 200 plus 800 divided by 2 is 500. Because 200 plus 800 is 1,000, divided by 2 gives you 500. So probability of having a claim that is less than 500 is 500 minus 200 over 800 minus 200 is 1/2. Or you can simply see that this is the midpoint, so the probability has to be half. And the expected value of P is just half times m of 3, which we calculated to be 6. And so this is equal to 3. Now, assume that events occur according to a homogeneous Poisson process with a constant claim intensity lambda on 0t, and suppose that independent of what has previously occurred, an event of type S, an event at time S is of type 1, is type 1 event with probability P1 of S, or a type 2 event with probability of 1 minus P1 of S. If n I of t for t greater than or equal to 0 denotes the number of type I events by time t, then n1 of t and n2 of t are independent, non-homogeneous Poisson processes with respective intensity functions equal to lambda times pi of t. And the expected values of these processes are E of n of I equal to lambda times the integral from 0 to t, P of I of S ds. Thus, we can thin a homogeneous process into a non-homogeneous Poisson process. Well, we'll kind of split it into two processes that are non-homogeneous. So assume a homogeneous Poisson process with claim intensity of 320 on 0.4. Assume we select randomly claims with chance of acceptance of t cubed over 64. What is the process of selected claims? What is the average number of claims selected by time to t equal to 2? So the selected claims follow non-homogeneous Poisson process on 0t, which is 0 to 4, with claim intensity equal to lambda times P of t. So it's 320 times t cubed over 64, which is 5t cubed. The mean number of claims selected by time 2 is the integral from 0 to 2 of lambda of t, which later on we call m of 2, but in this case, it's just calculated directly. That's equal to 5t to the fourth over 4. That's the function whose derivative is 5t cubed, evaluated from t equal to 0 to t equal to 2. At 0, it's 0. At 2, 5 times 2 to the fourth is 5 times 16. Divided by 4 makes it, well, I'm trying to do it in my head, but it's not obvious. 16, right. Okay, yeah. Actually, I'm making it too complicated. The t to the fourth is just 2 to the fourth, which is 4 times 4. So we can cancel 1 4, and then 5 times 4 is 20. Now here is an exercise from an actuarial examination. Beginning with the first full moon in October, deer are hit by cars at a Poisson rate of 20 per day. The time between when a deer is hit and when it is discovered by highway maintenance has an exponential distribution with a mean of 7 days. The number of hits and the times until they are discovered are independent. Calculate the expected number of deer that will be discovered in the first 10 days following the first full moon in October. So let n of t denote the number of deer hit in the first t days following the first full moon in October. That n of t is a homogeneous Poisson process with parameter lambda equal to 20 and mean lambda t. Each deer hit by time t can be classified as type 1, and deer hit and discovered by time t as type 2, deer hit and not discovered by time. All right, so we split this deer hit by time t into type 1 event when it's discovered and type 2 event when it's not discovered. Each deer hit at time s with s less than or equal to t is classified as type 1 with probability of p1 of s equal to f of t minus s, where f is the cumulative distribution of an exponential distribution with mean equal to 7, and 1 minus that is the other classification, because discovery has an exponential distribution with a mean of 7 here is given. Thus we have n of t is decomposed into n1 of t plus n2 of t. And E of Ni of t is lambda times the integral from 0 to t of pi of s ds. Since the number of hits and the times until they're discovered are independent, the processes are independent. We need to compute the expected value of n1 of 10. Well, we have E of n1 of 10 equal to 20 times, 20 is the lambda, times the integral from 0 to 10 of p 1 of s, which is f of 10 minus s ds. The cumulative distribution of the exponential random variable with mean 7 is known, and this is equal to 20 times the integral from 0 to 10 of 1 minus e to the minus 10 minus s over 7 ds, and that's equal to 20 times s minus 7 times e to the minus s minus 10 over 7 evaluated from 0 to 10. And then that's equal to 20 times 10 minus 7 plus 7 e to the minus 10 over 7. And that's approximately 93.55 and approximately 94. Now, in this next example, consider a non-homogeneous Poisson process with claim intensity lambda of t equal to 1 over 7 plus t. We will ask some questions about it. What is the mean number of claims expected by time 5? So remember, lambda of t is 1 over 7 plus t. So m of 5 is the integral from 0 to 5 of lambda of t. So integral from 0 to 5 of 1 over 7 plus t dt. The integral of that is natural logarithm of 7 plus t. We need to evaluate it from 0 to 5. That's a natural logarithm of 12 minus natural logarithm of 7, and it's approximately 0.5390. What is the mean number of claims expected from time 2 to time 5? That's m of 2 minus m of 5. So it's natural logarithm of 7 plus t evaluated from 2 to 5. That's natural logarithm of 12 over 9, and that's equal to 0.2877. It's also natural logarithm of 12 minus the natural logarithm of 9, but that's, well, that's the same thing. What is the chance of observing exactly 2 claims between time 2 and time 5? Well, it's a Poisson distribution with mean m of 5 minus m of 2, which we calculate to be 0.2877, and the probability is that parameter, that mean, so lambda, but lambda is 0.2877, lambda squared over 2 factorial e to the minus lambda. That's how Poisson distribution works. And that's approximately equal to 0.031. And what is the probability that the waiting time until the 4th claim is less than 10? Well, the number of claims from time 0 to 10 is Poisson distributed with mean m of 10, which is the natural logarithm of 10 plus 7 from the form of the calculation we did before, minus natural logarithm of 7, and that's 0.8873. The probability of observing 0 claims is e to the minus lambda with this lambda. The probability of observing I claims is lambda to the I over I factorial times e to the minus lambda. So probability of observing 4 or more claims is 1 minus the probability of observing 0, 1, 2, or 3 claims. And that's approximately equal to 0.0128. Now let S4 be the waiting time until the 4th claim. What is the density of S4 at time t equal to 10? Recall that let's just recall the generalized form of the formula for the gamma distribution. This is the form where m of t is integral from 0 to t of lambda s ds, lambda of s ds. So we get this if we plug it into this formula. Since lambda of s is 1 over 7 plus s, we have m of 10 equal to natural logarithm of 17 over 7 or 0.8873. And therefore, the value at 10 is 1 over 10 plus 7, so 17, e to the minus 0.8873 times e to the 0.8873 over 3 factorial, and this ends up being approximately 0.00282. So all this struggle about these Poisson processes is for the purpose of creating what is called the compound Poisson process, which is the most standard model for the total amount of claims made in property casualty insurance. A stochastic process is called a compound Poisson process if it can be represented as S of t equal to x1 plus x2 up to x big N of t, where x1, x2 are and so on are independent, identically distributed, and we commonly write IID for independent, identically distributed random variables with cumulative distribution function p of x. They are also independent of N of t, and xi is typically the random amount of the ith claim. N of t is a Poisson process. For insurance applications, N of t is the random number of claims in time period 0t. For a compound Poisson process, the distribution of the difference of its value at time r plus h and r, which is written as h as r, is also compound Poisson, and the probability that this random variable is less than or equal to x is of this form, where p star k of x is the cumulative distribution function of the sum of k independent identically distributed random variables with common cumulative distribution function P of X, where P refers to the probability distribution of these individual claims. And at any time t, the probability of the next claim occurring between times t plus h and t plus h plus d h, and being of amount not greater than x, is given by the expression e to the minus lambda dh times lambda dh p of x. The process has independent and stationary increments, and that is the aggregate claims on disjoint time intervals are independent random variables, and the distributions of each of these variables depends on only the length of the corresponding time interval, not location. And now we have kind of crucial results that if we write P1 equal to E of X, P2 equal to E of X squared, then the expected value of S sub t is equal to E of X times E of N of t, and that's lambda t P1, P1 being the expected value of X, and P2 is the second moment, and the variance of S sub t is equal to the variance of X times E of N of t plus variance of N of t times E of X, the mean squared, and that's equal to P2 minus P1 squared times lambda of t plus lambda t plus lambda t times P1 squared, and this ends up being just lambda t P2. P2 again is the second moment of X. In other words, E of S sub n, S sub t is equal to lambda t E of X, and the variance of S sub t is equal to lambda t E of X squared. Now here is an exercise applying this. People arrive at the food bank at a Poisson rate of 10 per day. 80% of them donate non-perishable units of food, and 20%, question. I'm not sure what you, help me. So the question is, what do the locations of the variables refer to? I'm not sure what you mean by the locations. The distributions of each of these variables depends on only, okay. That now I understand what you're saying. So let's go back to this. And for example, look at this distribution of S of R plus H minus S of R. So this distribution, we are saying, I'm going to take this thing and try to put it in the spot where we, let me try to find the word location. There we go. Okay, there we go. This is the spot you were asking about. So in other words, distribution of, okay, now I need to open my formula thingy. Okay. So the distribution of S of R plus H, and my word is slow. Okay, S and the distribution of S of H minus S of 0. Okay. This time location refers to location in time when this happens. When things happen, the time. So in other words, the distribution of S of R plus H minus S of R and S of H minus S of 0 distributions are the same. So that's this point about these stationary decrements. The concept stationary decrement means that things that happen between time 0 and time 1 follow the same probability distribution as things that happen between time 10 and time 11. It's only how long the period we're observing is that matters, not where it's located in terms of time. So whether it's at 0 or at 10, it doesn't make any difference. Does that make sense? Okay, thank you. All right, thank you very much. And let's continue with this. Okay. Individual food donations are distributed with mean 15 and variance 75, and individual withdrawals are distributed with mean 40 and variance 533. The number arriving and the amounts of donations and withdrawal are independent. Using the normal approximation, calculate the probability that the amount of food units at the end of 7 days will be at least 600 more than at the beginning of the week. So let S sub D and S sub W denote the cumulative amount of donated or withdrawn food at the end of the week, respectively. Similarly, let N sub D and NW denote the number of donations or withdrawals of food at the end of the week, so after 7 days, respectively. Let X denote an amount of a single donation of food, and similarly Y for withdrawal. And we have S sub D equal to X1 plus X2 up to X and D, and S sub W equal to Y1 plus Y2 up to Y and W. And S and D and S sub D and SW are two independent compound Poisson processes. Furthermore, E of X is 15, variance of X is 75. E of X squared is variance plus square of mean, so 300. E of Y is 40, variance of Y is 533. And E of Y squared, the second moment, is the variance plus the square of the mean, so 2133. From the Poisson decomposition theorem, ND and NW have Poisson distributions with means E of ND equal to 7 times 10 times 0.8, 7 days, 10 the mean of the underlying process times 0.8, the probability that it's a donation. And that's 56, and E of NW the same way, 7 times 10 times 0.2, and it's 14. Now we compute the expected value and variance for compound Poisson processes SD and SW. E of SD is E of X times E of X ND, so it's 15 times 56, it's 840. And remember, this is that theorem that I gave you, that it's the mean of the Poisson thing times the mean of the mean of the counting thing times the mean of the claim, and the second moment of the claim times the mean of the counting thing. So it's 15 times 56, so it's 840, 40 times 14, so it's 560. The second moment of X is 300, so it's 300 times 56, 16,800. Second moment of Y is 2133 times 14 is 29,862. And we need to compute the probability that S sub D minus S sub W is greater than 600. Now, both SD and SW can be approximated with a normal distribution because they are sums of independent, identically distributed random variables, and they are independent. So their difference is also approximately normal with parameter, they're all independent. So every time you add or subtract normal random variables, if they're independent, the sum is normal, or the difference is normal. The mean of the difference is 280. And the variance of the difference, because they're independent, the variance of the difference is the sum of the variances. And so we get 46,662. Therefore, denoting a standard normal random variable by Z, we have the probability that S sub d minus S sub w is greater than 600 is equal to the probability that S sub d minus S sub w minus its mean, which is 280, divided by its standard deviation, which is the square root of 46,662, is greater than, the right-hand side is 600, but we have to subtract the same thing to keep the inequality valid. So we subtract 280, like on the left-hand side, and we divide by the square root of 46,662, like on the left-hand side. And this becomes the probability that z is more than 1.48, which is 1 minus the probability that z is less than or equal to 1.48. So 1 minus 5, which is the cumulative distribution function of a standard normal random variable. And now this number, you can look it up in the table or use Excel to calculate it, or a calculator if you have a calculator that calculates this, and that's approximately 0.9306. So 1 minus 0.9306, and it's equal to 0.0694.